This is video 5 of Unit 1, and this video will talk about something called scientific notation. You may have learned about scientific notation before. We'll review it here and give you some more rules. What you see a picture of here is a virus. Now, viruses are really tiny. So if you want to take, say, the mass of a virus, you'll have to use extremely tiny numbers. And instead of saying 0.000 and having to write a lot of zeros down, we'll actually report it in a different way. So instead of saying 2, 5 or something like this, there's an easier way to report mass using scientific notation, and that's what we'll talk about here. So here's how it works. Scientific notation, what you would do is you would count how many decimal places to the first number. So usually we'll go back to the first number, and then we'll rewrite the significant digits, as you'll see, and then followed by a times 10. Now the reason why we use times 10 is because, remember, our system is based on metric, which is base 10. Metric is 10 based, so every time you multiply by 10, it's going to be like moving the decimal place over one more time. So that's what the metric system is about. And then we'll put a number in this little box. It'll be times 10 to the 5th, for example. That's how it will work. Now for big numbers, if you have a big number, like 93 million, this, by the way, is how many miles from here to the sun, 93 million miles on average. If you want to write this using scientific notation, what you'll do is you'll take the decimal places sitting at the end right here, and you'll start counting, go back and start counting until you get to the first number. So we'll do 1, 2, 3, 4, 5, 6, 7. So we've moved 7 times over all the way to the first, till after the first number. Notice we stopped after the first number. Then we'll do times 10, and we put the 7 in the power. So here it says big numbers, like 93 million, have positive exponents. So make sure, you don't have to put a plus here, you could if you want, but just 10 to the 7th. Whereas small numbers will have negative exponents. So you take a number like this, you'll begin here, and then move until you get over to after the first number. And that was 1, 2, 3, 4, 5, 6. That was 6 times. You rewrite the significant numbers. The significant numbers here are 1, 5, and 3, with the decimal place following the 1. Then times 10, notice to the negative 6. It's a negative number because small numbers have negative exponents. So anytime you go to the left, you'll actually make it more negative. And then if you go to the right, you'll make it more positive for the exponents. So hopefully that makes sense. Let's go ahead and do some example problems. So we want to rewrite these in scientific notation. So here we have a big number. We'll pretend the decimal place is back here and start moving until we get to after the first number. So let's see how many that is. 1, 2, 3, 4, 5, 6, 7, 8. So we moved 8 places. We can take a note of that. We'll rewrite just the 6, the 5, and the 3. Those are the only significant ones. So 6.53, and then times 10 to the 8. Simple as that. Here we have a small number. So we take the decimal place and move it until we get to after the first number and count. 1, 2, 3, 4, 5. So it took 5 steps to get there. And then we rewrite the 4 and the 5. So we'll write 4.5 times 10 to the, and don't forget it's a small number, so negative 5th. You've got to make sure you have that negative exponent there. Simple enough. Hopefully that makes sense. Go ahead and try a few on your own. Stop the video and try these two. And then let's finish up, like we did last time, with some calculations. Oh, I've got, I'm sorry. Let's do this one together. I'm sorry. Let's go the other way, and then I'll let you do the practice problems. This is example 6, so we're still doing this one. So here we're going the opposite way. We're actually going to write the regular notation out. So we're going backwards. Sorry there. So let's do, we got 3.4 times 10 to the 5th. Now what we'll do is we'll move now, since this is a big number, we'll move this to the right. We'll move the decimal place all the way out to the right, 5 times to the right, and then we'll see how big the number is. So just start writing this number. So we got 3.4. The decimal place was right here. We're going to move it 5 times. 1, 2, 3, 4, 5, and then we'll fill these in with zeros. So we actually have 4 zeros here. Let's rewrite the number so it looks a little cleaner. So we have 3, 4, and 4 zeros, which is actually 340,000. And that is how you would write a a regular number out from scientific notation. The second example has a negative exponent, so this is going to be a tiny number. So we'll actually move to the left, because remember, tiny numbers have negative exponents. So to begin with this one, usually you write, we got 8, 4, 3, 3. We begin right here, we're going to move 7 to the left. So 1, 2, 3, 4, 5, 6, 7. That's where the decimal place goes. We'll fill these in with zeros, and in this case we end up having 6 zeros. And let's rewrite this. Now I also would recommend putting a 0 in front of the decimal place. That way you can see it a little better. So let's rewrite this. So we got 0 point, and then we got 6 zeros here, and then the 8, 4, 3, and 3. And this is your final answer. Notice a positive exponent gave you a big number, 340,000. A negative exponent gave you a really, really small number, a few billions. Okay? So now you can try the practice problem. I actually have one of each. Oops. Okay. Let's talk about operations with scientific notation. So whenever the rule says if you multiply numbers, you would add the exponents. This rule actually comes from algebra. Anytime you're multiplying numbers with exponents, you get to add the exponents. So this 2 and this 5 get added up to give you a 7. Now, the numbers themselves still get multiplied. The 3 is multiplied by the 2 to give you the 6. So you still get 6 when you multiply the numbers, but the exponents get added. Very similarly, whenever you're dividing numbers, you divide the numbers. So the 3 divided by the 2, 3 divided by 2 is actually 1.5. But then you would subtract the exponents. So you do 5 minus 2, and that's how you get the 3. Notice that you still write out the times 10 in each case, and hopefully that makes sense. So why don't we try an example with this? Well, before we try the example, how about addition and subtraction? The second rule talks about adding and subtracting, and here the rule is really interesting. It says you ignore the small number unless the exponents are the same or if they're close. And close meaning about 3 orders of magnitude. Orders of magnitude, which means 3, so like if one number was, say, 10 to the 7th, and the other number was 10 to the 4th, now that's known as 3 orders of magnitude, 3 times away, so then you can't ignore. But it's really interesting. The reason why you ignore the number is because of significant figures. So an example here, we have 3.0 times 10 to the 6th. This is actually 3 million. This number, if you write it out, this will be 3 million. Now 2.0 times 10 to the 2nd is actually 200, simply 200. So if you have the number 3 million and you add another 200 to it, well, significantly, it will not make a difference. So you actually end up ignoring the small number, and you simply write the 3 million number, and that's simply your answer. Now notice that the order of magnitude here is between 2 and 6, which is 4 orders of magnitude, which is too much, so you can actually end up ignoring it. Similarly, if you subtract, this last example shows subtraction. This is also 3 million. If you do 3 million minus 200, same idea, you still get 3 million. Again, you ignore the smaller number. So with addition and subtraction, you ignore the smaller number. Now, if they are close, if they are within 3 orders of magnitude, you'd probably have to write them out, add them or subtract them, and then put them back in scientific notation. And we'll probably do an example of that in class. So here is for you to practice. This is just a practice problem since we've done it. Go ahead and try this on your own. Hopefully this makes sense. This concludes video 4, or video 5 rather.